Hi class, welcome to our lab for multiple regression assumptions and hierarchical regression. I have a couple helpers with me today. We have Curly right here. She's wondering what we're doing. And I have Sammy, but he's too big to pick up. So we will get started. What we're covering with this lab is to introduce looking at model level assumptions, and that's looking at if the residuals themselves are normally distributed, that they have no linear relationship with the predicted values, and that they are equally distributed as far as homoscedasticity. So we're looking at these assumptions related to regression, and we'll start with a review of multiple regression to get us into that so that we have a model to use. And then afterwards, we're going to conduct a hierarchical regression, which is when we're controlling for some of the variables that are not part of our focal attention. And we'll go through it as we move along. This is our lab sheet, so go ahead and have that open. And then what I'm opening is the survey.sav from Palat. Again, we'll review multiple regression and use that to look at model level assumptions. And then we'll move into the hierarchical regression, which is the new regression that we're learning in this lab. So first, I'm going to open up survey.sav. And it's just an SAV file, so I can just open it. I don't have to import it. Here we go. We got some output. We got the data set. I think I'll just put that right there. Okay. So of course, in the beginning, you look it over, you make sure that the variables are correct. The only one I'm going to worry about here is the ID variable. I'll turn it to nominal. I'm not using the categorical variables today, so I'm not going to worry about them, but I am making sure that the other variables we're using are at scale, so that's good. So when it comes to preliminary, I'm not going to run through preliminary analyses again because we've already done it a few times now. But you still do it for your homeworks. Basically, describe the data set and the variables of interest. You do your univariate assumption checking, which is the normal distribution of the predictor and the criterion variables, especially when they're continuous, using the histogram to look at, to visually inspect, and Shapiro-Wilks to test. And when we're talking about continuous predictors and a continuous criterion or outcome, you're also checking out bivariate linearity between each predictor criterion pair. So you look, you visually inspect the scatter plot, and you test it with the correlation test. So I'm not doing those again in the video. You can go back to our multiple regression video to go through that again. But you do want to do this anytime you're doing these types of analyses where your predictors are continuous and your outcomes continuous. But moving on, we're going to review multiple regression real quick. We're just going to pull a multiple regression to predict perceived stress being predicted by perceived control of external events and perceived control of internal states. So PCOS and TMAST. So we're going to just run the multiple regression first with those two predictors and the one outcome of total perceived stress. And then we're going to redo it afterwards to look at the model level assumptions. So to get our first multiple linear regression, I'll go to Analyze, Regression, and Linear. On here, I want total perceived stress as the dependent variable. And I want total mastery and TPCOISS as my independent variables. And that's all I'm going to run for right now. I'm going to paste this so that we get our syntax started. And run from syntax. Now we have our output. So just like interpreting before, we look at our f-test to tell us about the model. The model is significant. There's our f-test estimate, our degrees of freedom, the significance level, the r-squared as far as the effect size, and then I would have to go to Daniel Soper to get the confidence interval for the model. And then in the coefficients, I have the regression coefficients, the unstandardized coefficient, and the standardized or beta. Both of my predictors are significant. For every 1 unit change in total mastery, total stress changes by -0.62. And for every 1 unit change in PCOS, my total perceived stress is correspondingly changing -0.18. And that would be similar to our little write-up there with our regression coefficient, our significance level, and the effect size in standardized regression coefficient beta. So that's all review. We've done that before. And what we're moving into is how to check the regression diagnostics of the model itself. So now we're moving past checking specifics about a variable or the correlation of a variable. We're looking at what is going on with the residuals. And residuals, what are those? You know what? I'll go into that in a minute after we get some regression diagnostics. So we're going to go back to that dialog box where we got the regression at, and we're going to add a few more things into it. So analyze, regression, linear, and that's what we set up before. In the statistics submenu, it should already have estimates and model fit, but I'm also going to want case-wise diagnostics, outliers outside of 3 standard deviations, and let's see if I want anything else. We want descriptives, and we then go over to our residuals area. So estimates, model fit, and descriptives, and then down here in residuals, the case-wise diagnostics. And I can hit continue here. In plots, I'm going to want the histogram and the normal probability plot. Continue there. In save, I'm going to get some new variables here. I want predicted values unstandardized, residuals unstandardized, and Cook's. Cook's D is a indicator of outliers or something that might have influence on our regression. And I think that's it for that. Let me double check. Yep. Shh. We can continue here. And let's see if I wanted anything else. Nope. So now we're going to paste and run this from syntax. Okay, it's running that. It ran the same regression, but now with more information. We have our descriptives, the mean and standard deviation of each of these, both the outcome and the 2 predictors. We have the correlations between the three. The same model summary, ANOVA, and coefficients that we had before. But now we have this area down here with case-wise diagnostics and residual statistics and some plots. Okay, let's take a look at these. So what are residuals? We've talked about this in class, where residuals are the difference between what we predicted and what was actually there. If I had a score of 3, but I was predicted to have a score of 5, then the residual is 2. It's the difference between what was predicted and what was actually the data. Let's take a look at this in the data view itself. We're going to look at these new variables we made, which is the unstandardized predicted and the unstandardized residual. So going to the bottom, we have, oh, let me stretch this out so you can see it a little bit better. There you go. There's unstandardized predicted, unstandardized residual, and Cook's distance. And these were the ones that we saved when we went to the save sub-dialog box when we asked for these regression diagnostics. So going here, actually, let me go back a second. Remember that our outcome is total perceived stress, right? Right there. I'm going to just move it down a little bit so that I have it right beside the regression diagnostic variables so that we can look at them together. So I have, this was the actual, what was measured in total perceived stress. Here's what was predicted. Here's the residual. Now, I'm just going to get a quick calculator out here. So if this case had 29 actual perceived stress, but I'm going to subtract here, our equation, our prediction equation, predicted that they would have 28.26128 equals 0.73872, which is the residual. So all of these, the actual subtracting the predicted is going to equal the residual. And remember, when we're doing regression, ordinary least squares, it's looking for how it can minimize the errors. So there's going to be some above the predicted equation, some below the predicted equation, but that predicted equation is minimizing the errors on both sides, the residuals on both sides, for the whole line. But rarely does anyone actually land on the line. And that's those regression diagnostics of the residuals themselves. Okay, so how are we going to use these new variables to check out the model level assumptions? Well, let's talk about them. Multicollinearity is the first one we'll work with. And this refers to when the predictors are too highly correlated. When you have predictors that are too much related to each other, they might be looking at the same, they're just explaining the same variance in the outcome. And the regression model looks at their unique variance, right? But if they're not contributing anything more because it's almost the same as the other predictor, then it doesn't have any use in being in that model. And the way we can tell is by looking at what is the relationship between the predictors. Well, we asked for this in the descriptives table when we asked for descriptives between mastery and PCOS. And what is too high? Too high would be correlations greater than 0.9. So let's go look at that descriptives table in our output. We have the mean and standard deviation, but here's the correlations that it gave us with those descriptives. And it looks like we have a -6, 5.8, and a 5.2, 5.3. So nothing is up to 0.9, and especially our predictors, because really that's what we're looking at from multicollinearity, is what is the relationship between total mastery and PCOS. It's 0.53. So not a problem there, because 0.9 would be where we're saying it's no use having that second predictor. It's almost the same as the first one. Now, singularity refers to when the items in the model are kind of getting double tapped. Let me show you what I mean. When we look at the data view, or the variable view here, and see how total mastery is made up of, I think it's, there we go, all of these. So these 7 items, masked 1 through masked 7, is what are the items that went into the scale of total mastery. If I had these items in the regression with total mastery as well, right there. So if I had items and the total, which the items went into the total, then I'm having them in that equation twice, right? I don't have a single instance of those mastery items if I had items in the equation and the total mastery combined scale score, and that would be a violation of singularity. You could also see it if any of the items that went into total mastery were also items that went into PCOS, and it would be not singular. They would be represented more than once in that regression, like kind of hiding. And we don't have that because all of our mastery items are just in total mastery, and all of our PCOS items are only in total PCOS. Okay, so it's more of a design and making sure that you build your scale score right. It's not something you really test for with the regression diagnostics. But that's what singularity refers to. Okay, so let's take a look at outliers. And those are those very high or very low scores that differ substantially from the main trend of the data. There's 2 ways we're going to look at this. We can look at a scatter plot, and we're actually going to ask for the scatter plot a little bit later, right there. But I'm going to go ahead and call for it now so that we can see this. I want the scatter plot between predicted values and residuals. So I'm going to go, just like any kind of scatter plot, we can just go to Chart Builder and ask for a scatter dot, simple. And I'm going to put my predicted values on the x-axis. And I'll put my residuals on the y-axis. And I'm going to hit OK. You don't have to paste the Chart Builder syntax because we'd never be able to work with that syntax anyway. Okay, so now I have a scatter plot of unstandardized residuals by unstandardized predicted values. When I double click this and get it into an editor, I can do a couple of things here. I can identify which label things are. I can label using the data label mode and go hang over any of these that seem like they're really far out, like we said. A outlier is very high or very low scores that differ substantially from the main trend of the data. So looking at that, I'm saying, what about this little guy out here? That's number 364. Here's a number 18. Here's 55. And those are ones that kind of seem to stick out furthest from the trend of the data in the middle. I'll leave it open for now because we're going to add another thing here in a minute. We also, well, I'll close it so we can see something else here. I'll close it for a second. It keeps our labels, so that's nice. But up here in our case diagnostics, it says that case 55 had more than 3 standard deviations on the standardized residual. That's not what we plotted, but it's just standardized. And more than 3 deviations away is something that's like really standing out. It says the residual was negative 14.8, and that was really far away from what it was expected to have. So that is saying that that SPSS identified one potential outlier there, and we found it. Number 55 was that one down there. So it did not say that these two, number 18 and number 364, it did not identify those as being very far away as far as more than 3 standard deviations away from what it was expected to be. But it said that this one, case 55 there, was pretty far away. And we're going to check that one out, but there's another way that we can use to find out about outliers, and that's that Cook's D that we asked for. It's called COO_1 in our new variable. So we're going to go check that out. If we organize this ascending and descending, like ascending, the lowest is like 0, no problem. How about descending? So the highest is 0.095, and the cutoff is values greater than 1 for Cooks. So this one right here at 0.095 is the one with the residual of negative 14.84. That number look familiar? It's the one that was identified right there. So that residual of negative 14 is the one that has the Cook's distance of 0.095. So it's still less than 1, which is another way to identify outliers. So even though it was more than 3 standard deviations according to the regression diagnostics, I'm not going to worry about it because the Cook's distance is less than 1. So there's usually different ways to identify things. And if you look in your Palant chapter for this, it goes over a lot more regression diagnostics that you can look at, but we're just covering a few of the basics. The next thing we're going to check out is the normality, linearity, and homoscedasticity of the residuals. So when we were looking at univariate assumption checking, we were just checking this for a particular variable. Here we're actually looking at these characteristics of the residuals themselves, of those error terms. Normality says that the error terms should be normally distributed. Just like any time that we look at normal distribution, it's easy to just ask for a histogram. The residuals, since we asked for the new variable, that's the residuals, we can just get a histogram of the residuals. And that's one way to visually inspect those. Let's take a look. I'll go to Chart Builder, and I'm going to clear this by hitting Reset. And I'm going to go to Histogram. Just want a basic histogram. And then I'll go to the residuals and pull that over. And I'll hit OK here. There you go. There's my histogram of residuals. Looks pretty normal. Compared to some of our other charts, that's more normal than usual, right? Another way that we look at normal distribution is with the normal PP plot, and we'll see in our studio there's a normal QQ plot. They're very similar. But SPSS gives us a normal PP, which is this one right here. The diagonal line, like the straight diagonal line, that's the predicted expectation of the residuals, whereas the dots are the actual residuals. So when you see deviation away from that line, that's telling you that that's going away from normal distribution. And you see we don't deviate that much. And those are visual ways to check out normal distribution. What was our test of normal distribution? The Shapiro-Wilks test, which we can get to by using the explore function, right? Back to analyze, descriptive statistics, explore, and putting that new, we want residuals. Are the residuals normally distributed? And finding our, not that one, not that one. There it is. Under plots, normality plots with tests. And I don't need the plots themselves. I just want the test. I'll paste this just so that I have it. There we go. There we go. We have tests of normality, Shapiro-Wilk. So it came in significant. I wasn't expecting that. So I would report that Shapiro-Wilks was significant for the residuals, but it doesn't look significant in that diagram, huh? In the histogram or in the PP plot. So normal distribution of the residuals says that they should be normally distributed. And we can do that with a histogram, we can do it with the normal PP plot, and we can also ask for a Shapiro-Wilks test. Linearity, that's the next one we're going to work with. Linearity is saying, are the residuals related to the predicted values? They shouldn't be, because if they were related to the predicted values, they would be part of whatever variable was in the model. So if we have residuals that are related to the predicted value, it pretty much means we have a predictor that's not being accounted for in that equation. So we're hoping that there is no relationship between the residuals and the predicted values. But the way we look at relationships between two variables is looking at the correlation, right? And we look at visually with the scatter plot, which we already pulled earlier. So we're going to go back to that right there. Do we see a linear trend, like a positive relationship, a negative relationship between the predicted values and the residuals? Not really. We can also ask for the correlation between those two. So analyze, correlate, bivariate, just like I think that was correlation and multiple regression lab. Is there a relationship between those two? Go ahead and paste and run from syntax. So we have 0, 0, 0, 0, 0, 0 between the residuals and the predicted values. When you see all those zeros, you can double click on it and get to what is the full number there. There it is. So 1.6878 to the negative 16th power, which is 15 zeros, like 15 zeros and then 16878. It's practically 0. So there is no relationship being identified between the predicted and the residuals. Just like when you checked bivariate linearity of your predictor and your outcome, and there you are looking for a significant correlation. Here we're hoping there is no relationship between them so that we have not violated linearity of residuals. We want them not to be related between residuals and predicted values. Alrighty, one more here. Homoscedasticity is saying that the residuals are distributed similarly for all predicted values. And it's helpful that we can visually inspect this with the same scatter plot we just picked up. So what we're going to do with that is add a reference line. So I'm going back to my scatter plot right there, double click to open it up in the chart editor, and I want to add a reference line to the y-axis. I want the reference line at 0. And it usually opens up just on 0, but if it's not, you want it on 0. So close that, and there's the line right there. I can make it a different color. Let's see. I'm sure I can make it a different color so it's easier to see. Maybe that'll do it. Maybe something like green and maybe a little bigger. Yeah, like that. Cool. So when we're looking at this, is the spread, like if I look at each predicted value, is the spread of residuals above 0 similar to the spread of residuals below that 0 line? So on any predicted value, is it kind of spread similarly over and under that reference line at y equals 0? I don't see any major issues with distribution there. And we're not going to test that one. So you just do your visual inspection and report that. Okay, we got our histogram, we got our case diagnostics. So we've got everything. We've checked out all of these different model level assumptions. We looked at multicollinearity. Singularity we talked about, it's not really a test, it's just how you make sure that you're not putting an item into the equation more than once. Outliers, we looked at those a couple of ways, and we looked at normality, linearity, and homoscedasticity of the residuals. But how do you include that in a write-up? Well, you typically put it as either the end of your preliminary analysis or the beginning of your model. You let the reader know that you checked out the assumptions of the model, assumptions of regression. And here I give you a little example on what that might look like. You can give the reader some figures, especially if you had a violation of an assumption. You would want to provide details on what you saw or did. And then you're ready to go on to your results. And like I said, we've already run multiple regression. The regression results itself are, basic. We have our model, the main model, and how much percent of the outcome was explained by the model. You talk about your regression coefficients, and the beta term, being the standardized regression weight, is the one that tells you the relative difference between those two predictors. In other words, right here, perceived control of internal states, or perceived control, had a lower beta effect size compared to the effect size of total mastery. So total mastery was a stronger predictor than perceived control when it comes to predicting total perceived stress. And there's our prediction equation. And like I said, we've already done the model, the multiple regression itself. What we added into it this time is checking those model level assumptions. So moving on, and this is a good place to pause and take a break if you would like to take a quick break there. We're going to learn a new regression. We're going to push into a more complex regression than multiple regression, and this is called hierarchical. You might also hear it called partial F test, or a not stepwise, that's different, but a per block or per step. But I usually hear it called hierarchical regression. And that's sometimes there's factors that could be contributing to the outcome that are not what you're really interested in. For example, maybe we think that age or social desirable responding is also related to perceived stress. But we just want to make sure any variation explained by those variables are not making it noisy that we can't see the effect due to total mastery and perception of control, perceived control. You would look at it like back in design, when we would place participants' random assignment to different conditions, it was so that we could control for extraneous factors, right? Extraneous variables or confounds, like, maybe having one group with all older people and another group with all younger people would be the difference in the outcome is due to age, not due to the actual treatment that we're doing in those two conditions. And that's when you're controlling at design stage. You're doing a random assignment to conditions to help control for those individual differences that might be just between participants. Well, sometimes, especially in applied research, you don't get to randomly assign to conditions, or you have limited ability to do that. So you can also statistically control for a variable or a confound, and this is how you do it. We would kind of filter out or have the unique variation that's being explained by some of these other potential confounds. We'd take those out of the model first in a step one, and then look at our predictors that we're truly interested in step two. And that's why it's hierarchical. We're doing it in steps. So what we're going to do with our hierarchical regression is show you how to put those into steps, but also request the assumption check information, the model level assumption check, because you can ask for them at the same time. But I just wanted to show you what we're doing with assumption check before we introduce a new regression. So going back to SPSS, we're going to analyze this regression of if we control for age and social desirable responding first, is our set of predictors, total mastery and perceived control, still predicting total perceived stress? We'll go do that. Go to Analyze, Regression, and Linear. So I'm going to reset this so that I can just start from fresh. The dependent variable is total perceived stress. Which I know is here. There it is. Oh, I moved it down. And in block 1 or step 1, however it depends on, it might say step 1 if you're in a different version of SPSS, but this first block, we want age and social desirability. The T Marlowe is the social desirability scale, and age is up at the top in the demographics. And then now we're going to hit next, and we have block 2. This is where we're putting our variables that we're actually interested in: total mastery and perceived control. And now we're going to make sure we add in all of those regression diagnostics requests right here on the model instead of going back and doing it later. So we want descriptives and we want case-wise diagnostics. In plots, we're going to want the histogram and the normal probability. In save, we want the unstandardized predicted values, the unstandardized residuals, and cooks. And I think that's it. Let me double check. We need R-squared change. Don't forget that one. Okay, all I gotta do is get R-squared change in the statistics block. Right there. So estimates, model fit, R-squared change descriptives, and case-wise diagnostics. Let's continue here. Paste. And I'm going over to syntax. So now we have all of that output again. The descriptives, the correlations, and again, looking at total mastery and total perceived control. Is there a relationship between them? It's still 0.53. In fact, the highest one here looks like 5.8. So I don't have anything close to 0.9, especially between the predictors. So I'm not worried about multicollinearity. Let's look at, here's the model results in here as well. And I highlighted areas that we would use for our write-up here. Our F test, you're looking at step 2. You see how it says model 1 and model 2? Model 1 is where we only had the control variables, so age and social desirability. Whereas model 2 had all 4, had age and social desirability and total mastery and total perceived control. So the 4 predictors, that's the F test of the full model on model 2. Similarly, when we're looking at model summary, the R-squared, the effect size of that model, you want to make sure you're taking the information from the model 2 when you're reporting about the full model. And then we'll get the coefficients in just a sec. Right here, the change statistics is what you're checking out. Like for model 1 with just age and social desirability, the model explained about 5.9, almost 6% of the variation in total perceived stress. But when we came to model 2, we had an F change from 13 to 162. And this is the partial F test right here. That change for F was now 162.07 with degrees of freedom 2, 418. It was a significant change. And now the change in R square, sometimes you'll see that as a delta R squared, was 0.411. In other words, adding the two predictors, the total mastery and total perceived control, explained an additional 41.1% of the variation in the outcome compared to the first model. So a lot going on there. And that's before we even get to coefficients, like the regression coefficients. We have that in that second model, age was not significant anymore. Social desirability was not significant anymore, but total mastery and total perceived control still stayed significant. Okay. We'll get to the write-up. That's what you want to look at there for seeing where these numbers go into the write-up itself, because you report your partial F test and your full model. Let's scroll down and do that real quick. So age and social desirability were entered at step 1 and ended up explaining I put 5.7. It's just a little off because RStudio and SPSS are running it differently, but it's fine if you said 5.9 because that's what it is in the SPSS of the variance in perceived stress. So that's at step 1, right? That's here, this guy, 5.9 of the variance in perceived stress. That's model 1 with just age and social desirability in there. But we're not reporting all the coefficients for model 1. We're more interested in the second model, the full model. But we're letting the reader know what happened at step 1. And then after the entry of the other two predictors at step 2, the total of variance explained by the model as a whole, so that's the full model, was 47%. Let's see. Yep, 47.0 R squared. So that's the whole model R square on that side. Now we see, and that's the F test for the whole model. That 9267 is 9267 right there. That's when you're reporting the whole model. But now let's look at the partial F. Specifically, the two measures, total mastery and perceived control, explained an additional 43 point, that's again the difference between SPSS and RStudio there, explain an additional 41.1% of the variance in stress after controlling for age and social desirable responding. So now you're looking at this change statistics side. So the 162.07 right there, the 2,418 right there. So this one is your partial F test. And instead of R and the confidence interval for R, we have delta R squared. That's the change in R was 0.411. And that's why it explained an additional 41.1% of the variance. That's increased variance explained over and above controlling for age and social desirability. Then when you talk about your predictors, you're only talking about the two focal predictors at the in the final model. So coefficients, yes, right there. So total mastery and total perceived control. Now the only reason I'm not talking about age and desirability in this last one is because neither of them were significant. If it turned out that one of my control variables was still significant afterwards, then I would want to let the reader know. So in the final model, what are the significant predictors of perceived stress? And then in the prediction equation, I have all of the regression coefficients for the final model, model 2 here. And you could have more than 2 steps if you wanted to control for some demographics and then do the test of predictors that you're used to having, but then try out a new predictor. You would put that in a step 3 to see if there's also a change in R squared to that 3rd step. Okay, let's see. I skipped past checking out our model assumptions. So just like we did when I was introducing you to model assumption checks, you would check out multicollinearity. Are the predictors too highly correlated? We saw that in the descriptive statistics and correlations table, and we're looking at our predictors, mastery and perceived control. Looking at this right here, 530. So they are not too highly correlated. They're not anywhere near 0.9. So I'm good on multicollinearity. Outliers, I want to see if my Cook's distance is greater than 1, or I could also see if it pulled up on here. Case-wise diagnostics, it said this one residual negative 1473 might be problematic, and that's likely the one we saw before, but I had reordered the data set. Let's see, 1473. I can go over to the data, and I'm looking, because we ran it before, that's why it's got the 1. Here for this model that we're working with right now, it has a 2 because it's the second time I asked for those case diagnostic type variables. So for our current regression, I'm looking at the underscore 2. And I want to see Cook's distance, and I'm going to sort it descending. 0.05. It's nowhere near 1. And that's how I know Cook's distance cutoff. And then there's that residual, negative 1476, that SPSS identified as a potential issue because it's more than 3 standard deviations away from what was expected. But like I said, I checked the Cook's distance on it. It's nowhere near 1, so I'm not going to worry about it. I might say in my write-up that SPSS identified a potential outlier. However, the Cook's distance for it indicated that it's a non-issue. It doesn't have undue influence on the regression itself. And again, you might want to read through Palant on this because she goes over it in good detail. Okay, normality, linearity, and homoscedasticity of the residuals. So I can do the normal PP plot right here and see if just a little bit of variation off the line, and the histogram of the residuals doesn't look too crazy to me. And I can run Shapiro's Wilks on it. And if it comes out significant, that's fine. Just say Shapiro Wilks was significant. However, the plot does not look unduly non-normal. Or if you feel that the plot does look non-normal, that is pretty spiky right there, right? So maybe that's what Shapiro Wilks is picking up. And then linearity. Is there a relationship between the predicted values and the residuals? Again, we can just check out a scatter plot in Graphs, Chart Builder. I'm going to reset this and ask for a scatter plot. I'll put my predicted values on the x-axis and my residuals on the y-axis, and then say, okay. There's a nice scatter plot. I can find that one that was identified. It's probably the same one we saw before. Yep, it called it number 1, and there he is. I can add my reference line so I can check out, oh, I gotta turn off data label mode and then get my reference line. Let me go ahead and make it stand out a bit so I can see it. So I'm looking at heteroscedasticity. I'm seeing the distribution of residuals above and below that 0 reference line. But for linearity, do I see a positive or negative trend here between for each predicted value? So if I just look at, let's say 20, is it about the same here as up here on the distribution of the residuals? That's homoscedasticity. But if I'm looking for, do I see a positive or negative trend, I'm looking at, is there a linear relationship between predicted and residuals? And we can test that with our correlation test. Correlate, bivariate. I'm going to put these guys back and get the new number 2s. And paste. Oh, there we go. And very small. How small? 2.048 to the negative 16. Pretty much 0. So a correlation of 0 means no relationship is there. Alrighty. So we checked out that. What else? That's it. So going forward, all of your regressions, you're going to also check the assumptions of the regression, and that is looking at normality, linearity, and the homoscedasticity of the residuals, and also checking out multicollinearity and outliers. And the way we do it, we look at the correlation of predictors for multicollinearity. We look at Cook's distance for outliers, or if SPSS identified any, we check them out. And we have these methods for checking the normality, linearity, and homoscedasticity of residuals. We have all the information, and now it's time to communicate these results to the reader. What I have below is an example write-up, a table, and figures. And this does not include the preliminary, like the describing the data, describing the variables of interest. That you would do with your homework anyway, but I didn't want to take time in our lab video to do what you already know how to do. But here I'm kind of explaining what I did, what the regression was, and what looking at the model level assumptions look like. I think this was a 3. I think those are just little differences between RStudio and SPSS. No worries. And then this is our model information itself and our prediction equation. Here's the table. The table starts getting a little more involved as well. Here's our first regression with just age and social desirability. And then here's the second regression with the change in R squared. And then I picked a couple of figures to look at model assumptions of the residuals. Okay, that's it for our SPSS video. I will see you in class.